I'm glad to be here to introduce our recent work about the early development in the functional connectome based on a new method called multi-layer functional network. We developed this method, which actually is not very novel because previously a lot of people has used multi-layer network to analyze the social network or the temporal network or the dynamic functional connectivity. But we use such a method to investigate the individual variability, actually, which is very important for the brain development, because as we all know that not every single subject are the same, okay? So we're going to develop this method and to apply this method to reveal a new development pattern in terms of the modular structure. I'm from the University of North Carolina, Chapel Hill, and I'm glad to represent our group. Our group has been working on the infant brain development and infant MRI studies for a very long term. And as you may know, that we are launching a baby Connectome project recently, which has the DTI and resting state fMRI and T1, T2, and we are going to submit the data to CCF and all the raw data and the preprocessed data. So this is actually a pilot study of the BCP. So as we all know, the 4D fMRI data can be used to construct a brain functional network in a matrix, functional connectivity matrix form. And you can see that there are structures in that connectivity matrix, which we call it modules or the community. So here is a very simple example. You can see the functional connectivity within the modules more dense, and functional connectivity between the modules is more sparse. So each modules represent the specific brain function. So it's very important to investigate the module development in the very early life. For example, from neonate to the 1-year-old and to 2-year-old. So traditionally, for example, we have 3 subjects, and each of the subject has different functional connectivity matrix. And to get the group level functional connectome, we have to make a group average. And you can see that in the average adjacency matrix, you can see the functional connectivity is very blurred, which is not very good for the development study. Think about, we have a very blurred functional connectivity matrix at the neonate stage, and we have a very blurred functional connectivity matrix in the 1-year-old. So based on the blurred functional connectivity matrix, we can hardly detect the module development. So although it can show the group level community information, but it has a blurred information and it lost the individual community information. So we cannot use such a method to study the individual variability. So we proposed a method called the multi-layer functional connectome. We create interlayer functional connectivity between respective nodes across, between different pairs of the subjects. So for example, these 3 individual functional connectivity matrix can become a very big matrix, which we call it super adjacency matrix. And each subject functional connectivity matrix is in the main diagonal. And here is the interlayer functional connectivity. And based on this big matrix, we can get the modules information, and this module information can be both group level and individual level, so we can have the individual variability information. Okay. For example, these 3 brain regions have very consistent modular assignment, and these 2 also, but these 2 brain regions has a variable modular assignment across different subjects. We think this is very important because this reflects the individual variability. So let's introduce our method in stepwise. Firstly, we construct a multi-layer network by adding the multi-layer functional connectivity, And here we use omega to control the inter-subject constraint. And we also have another parameter, which is gamma, which controls the resolution of the module detection or the number of the modules being detected. And we use heuristic parameter optimization to avoid the randomly determine this very important parameters, because when you determine the parameters in a random way, in an arbitrary way, it will affect the result. And you can see for the neonates, this columns is different subject. You can see the functional. You can see the functional modules has very consistent across different subject. But you can see the individual variability in terms of the module assignment. Also, we repeated our method to the data of 1 year old and 2 year old. Of course, this is a longitudinal study. Each subject is the same. We scanned it for 3 times across the early development. So we can have the individual variability, for example here. So this region has a variable module assignment across different subjects. We can also have the color code, the consistent modules, which is very consistent across subjects. And we have the main result. Here we detect the 5 modules, and we use color code different modules for different age group. Here is the brain regions. We can also use the brightness code, the individual variability in terms of the module assignment across different subjects. By breaking down the main result into different view angle, we can get the spatial evolution. You can see some of the modules is expanding, some of the module. When we look at the module size evolution, some of the modules, for example, the visual network has been developing focalized or spatialized. And we can also check the individual variability, which cannot be done previously. So the individual variability has been reduced from the neonate to the 1st year old and then increased. Here's the consistent module for the neonates and 1 year old and 2 year olds. And we can also check the specific brain regions. For example, the brain regions here, which is in the neonate stage, they have a very consistent module assignment at the neonate stage, but it developed less consistent. You can see it developed less consistent in terms of the module assignment. So this area actually belongs to the default mode network and the striatal network. And we can also check the brain regions which has the increased consistency or the decreased diversity in terms of the module assignment. Also, these regions. And in summary, we developed a method called the melisma, which use the multi-layer large-scale functional connectome analysis, and we use this to study the module development in the first 2 postnatal years. We can have the group consistent module analysis, but and without losing the power of individual difference. And here we can see the novel information can be detected when consider the individual variability in terms of the development. Thank you.
We have time for some questions. Please come to the microphone.
Hello.
Hi.
Yeah, okay. Thank you for the very nice talk. I just have a question. Could you share with us how you chose your omega and your gamma parameter?
Yeah. I'm going to do that. So actually, the gamma and the omega is very important to choose because the gamma actually control the individual consistency. If we have a very large omega, then we will have the very same modular structure across different subjects. That is not realistic. So we use the normalized mutual information to calculate the variability in terms of the module assignment across different subjects. We don't choose this part because this part means every subject has the same module structure. So we just ignore this part. And also, we just investigate the number of the modules. We exclude the result with too small number of modules, which is not very realistic. So based on this heat map spanning two different parameters values, we can have this part of the regions being retained. And then we check the modularity Q and the module quantity K. And then we use some type of method to determine the center of the region, so represented by the star here. And we can see the star here very consistent across different age groups, which is actually omega equals to 1.3, gamma equals to 1.3, and omega equals to 0.3. So that's how we use the heuristic method to determine the parameters. Thank you.
Time for one more question.
Hi, I was just wondering, are you measuring neonates from gestational age or age following birth? And in particular, considering the rapidity of brain development, especially in those first few weeks and months after birth, how do you account for the tremendous variability in brain aging during that period?
Our subject actually is the term infant, so we don't look at the gestational age, but we just look at the age after birth. So they are actually within the first months after birth. But we assume that this subject has very little variability in terms of the gestational age because they are termed infant.
Thank you very much. Our next person, oh, yes.
Okay. And welcome to stop by our poster, and we can discuss more about the BCP data. Thank you.
Thank you.